So let's answer the question, what is the shortest distance between 2 points? Now common sense tells us in the Euclidean space here that the shortest distance is going to be a straight line. But we're going to have to go and prove that, and we'll prove that using the calculus of variations. So we've drawn out the 2 points here, a point A and a point B, and we can see that we've got an infinite number of different routes we can take in order to get from A to B. I've drawn 2 of them out there. Now I've split the lines out into small segments, and we'll call each segment here a small distance ds. So that's an infinitesimal distance ds. Now we've seen in one of the previous videos that whenever we did the catenary, that is the shape that a hanging rope sits in, that we were going to minimise a particular quantity. Now the quantity that we minimised in terms of the catenary was our 1 plus y derivative squared to the power of a half times y. In this instance here, we're going to ask the question, what is the term that actually gets minimised? Well, quite clearly we want to go from A to B using the minimum distance, so what's got to get minimised is the distance. So the minimisation is on the path length. So what is the path length? Well, the distance here is ds. The total path length is the addition of all of these small distances ds. That is, we've got to integrate all of these distances up. So what we want to minimise is the integral from A to B of our value ds. So again, we use the same process we did in the previous example. We think about this ds as being made up of a dx and a dy, and we use Pythagoras theorem, and because we're dealing with infinitesimal distances, this curve here will in effect be a straight line. So we're thinking about linearising this in terms of an infinite number of tiny straight lines. So we've got our ds squared is equal to our dx squared plus dy squared. We can divide through it by dx squared. We get our 1 plus dy squared to be dx squared. We can then take our dx squared up, and then we can take our square root of it. So we'll end up with a value of ds is equal to 1 plus y derivative squared to the power of a half. So this is a quantity here that's going to get minimised. So we can say then that the value s is going to equal the integral from a to b of 1 plus y derivative squared to the power of a half. So now we're going to exercise the calculus of variations on this little functional here. So let's go ahead and we'll do that now. So as in the example when we looked at the hanging rope, we found a simplification for the Euler-Lagrange equation. Now we've got a further simplification. We can see from this equation here that this functional here has got only an explicit dependence on y squared. There's no explicit dependence on x, and there's no explicit dependence on y. So that allows us to simplify this. So it allows us to simplify the Euler-Lagrange equation. Now again, if you go to the video called Beltrami identity, then you'll see that we have this minimization of the simplification of the Euler-Lagrange derived. So if you're interested in that derivation, you can go and have a look at that now. If not, you can wait and you'll see it later on in the course. So the simplification then is of this form here. So instead of using the partial f by partial y minus d by dx partial f by partial y derivative equaling 0, we can simply use partial f by partial y derivative equals a constant. So that simplifies the Euler-Lagrange equation quite considerably. So our function here, f, is our 1 plus y derivative squared to the power of a half. So we're going to differentiate this with respect to our y derivative. And again, we've seen that previously. And all we're going to have here is the chain rule for differentiation. So we're going to have a half of 1 plus y derivative squared to the minus a half, and then we differentiate what's inside. So that is 2y derivative equals a constant. So again, that can be written as c equals y derivative equals c1 plus y derivative squared to the power of a half. So when we take that across, it becomes the power of plus a half. So that can be written, if we were to square this side, we could square that side, get rid of the factor of power of half. So that's y derivative squared equals c squared, 1 plus y derivative squared. Now, what we can do is, we know that these values of c are just constant. So whether we call them c squared or c cubed or c whatever, it doesn't really matter. It's just a constant. So we don't need to write c squared. We could just replace that c squared with a value of k. So we could write that as y derived squared equals, and we multiply that out as k plus ky derivative squared. So then we can rewrite that in terms of our value of y derivative squared. So we take out y derivative squared, the common factor. We have 1 plus y, 1 minus k equals k. We can then take that value down. You get k upon 1 minus k. Now again, if we were to replace the whole thing here with a constant, because k is a constant, 1's a constant, minus k is a constant, so we can just call that whole thing one single constant, and we can give it a name. Now in this instance here, we'll give it a value of m, okay, because m and n will end up being our gradient. So we end up with our y derivative squared is equal to m. So in effect, we could also just write that as y derivative is equal to m as well, because it's just a constant. So then we can rewrite this as dy by dx, which is our y derivative, is equal to our value of m. So therefore we can say our dy equals m dx. It's a little differential equation, so we simply integrate both sides. So if we integrate dy, and then we take m out, then we'll integrate dx. So if we integrate dx, we just get a value of x, and of course our constant of integration, we'll call that c. So that's finally, we'll get the value of the equation, which is just going to equal y equals mx plus c, which is the equation of a straight line. So therefore we've proven using the calculus of variations that the shortest distance from 2 points in Euclidean space is a straight line given by the usual straight line equation y equals mx plus c. So again, don't take my word for all of this. Go back, go through it all, and re-derive it for yourself, and try sitting down with a blank piece of paper and just thinking through yourself and try to work through the derivation yourself without any notes. So thank you for listening. I'll get you in the next video. Goodbye.